Linux is a popular operating system for server administration because it's secure, stable, and flexible. In this course, Sean Powers from CBT Nuggets will detail every part of configuring, monitoring, and supporting a server setup that runs the Linux operating system. This course will teach you everything you need to know to configure Linux servers, including the boot process, kernel modules, network connection parameters, localization groups, and more. Let's get started.
BIOS and UEFI are two tools that basically do the same sort of thing, but they can be a little bit confusing when it comes to how do you know which one to use on a computer, and do I need to support one or the other or both? Or the nice thing is you usually either have BIOS or UEFI. Now, BIOS is an older program and it just stands for Basic Input Output System, whereas UEFI is the new kid on the block, and this stands for Unified Extensible Firmware Interface, which sounds confusing, but really it's just the way that we can interact between the hardware and the operating system. Now, let's say that we have two different vehicles. Now, these are two obviously very, very different vehicles. One of them is a sports car and one of them is an awesome yellow Volkswagen Beetle. I actually have a Volkswagen Beetle that's yellow like this, and it's awesome. But nonetheless, you could be a sports car person. Either way, even though they're ridiculously different vehicles, they both have some common interfaces, right? They're both going to have brake pedals. They're both going to have steering wheels. They're both going to have windshields, and those interfaces are fairly common across all vehicles. Now, the brakes in the underlying system are going to be different. This sports car probably has really nice disc brakes, whereas these old Volkswagens have drum brakes. Now, drum brakes aren't as good, but the interface itself is very, very similar. You push the brake pedal and you stop, and that's kind of what BIOS and UEFI are. They're interfaces between the hardware and the operating system itself. Now, they do work a little bit differently. So here we have our hard drive on our system. Now, using BIOS, like the old method of booting a computer, you would have like the very first sector on the hard drive would be the boot sector, and that's where the MBR, the master boot record, would live. And then that would tell the computer where the partitions are and point it to where to boot. Now, there's a lot of limitations with BIOS. You could only have 4 partitions using the BIOS and MBR combination. There are some hacks to get around that. They would take a partition and do extended partitions inside that, but that's a whole nother nugget. Still, there was this limitation, also a limitation of size with the drive. How much this boot sector or this master boot record can actually reference. It can be a small amount, like 2 terabytes instead of exabytes of data. And so UEFI is a replacement for the BIOS technology. And rather than just have the single boot sector, what it does is there's an entire partition on the system, and that partition is where all of the boot code is for whatever operating systems might be on the computer. So rather than just the boot sector pointing to, the rest of the hard drive, this is an actual specialized partition on the computer, and that's where the UEFI code is stored. Also, it uses a different partition scheme, so you can have tons and tons of partitions, and it can address a much larger hard drive. There's also other things like secure boot that UEFI supports that BIOS doesn't. Basically, just know that UEFI is the replacement for BIOS. It replaces the functionality of connecting the hardware to the software of the operating system. Now, the good news is if you have a computer that's older, or even some new ones still come with BIOS, you can still get around a lot of the limitations because there are hacks that will let you use really big hard drives, or hacks that will allow you to do some of the things that you can't normally do out of the box. But most computers now are coming with UEFI, and from an installer point of view, there's very little you have to do because the operating system is going to say, okay, I was booted using UEFI, so I'm going to create a partition, a UEFI partition, and I'm going to put all the boot code in there. So from your standpoint, from the end user or the installer standpoint, there's very little difference, but under the hood, a lot of new cool stuff is going on, and that's why UEFI is kind of the way of the future. Remember when you were a kid and in the doctor's waiting room, there were these magazines, and one of the games inside the magazines was that you had to find the difference in one of a bunch of similar looking figures. Like, for example, here are, what do I have? 9 different jokers, and one of them is a little different. Now, it's not terribly difficult to see which one is different here if you watched while they appeared. This one has a tiny little spot right there on his shirt that's different than all the others. So we've been able to identify it, but you can see they're very, 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 very similar. Well, the same thing is true about Grub and Grub 2, which of course is the next iteration of Grub. Now, Grub stands for Grand Unified Bootloader, but really it's just the way that the computer transitions from BIOS or UEFI booting up conditions into the actual operating system itself. It's what tells the computer, okay, where's my partitions and stuff like that. It's very easy to confuse which is which on your system, which seems silly, but it can be very, very embarrassing when you sit down at a system and you're like, okay, so is this running Grub or Grub 2? Because they do the same thing, right? They both boot the computer, but they do have some minor nuanced differences. Grub, of course, is older. You probably guessed that by it not having a 2 at the end of its name. But Grub is often called Grub Legacy because it is older, but it's still on a few operating systems. Not many, but a few. I think Slackware still uses Grub Legacy. Now, the biggest and easiest way to figure out if you're dealing with Grub or Grub 2 on your system is to look inside the boot Grub folder. And if you see menu.lst or grub.conf, that means you're running Grub Legacy because Grub 2 does not have those configuration files. Grub 2 has this configuration file, grub.cfg. Now, it's easy to confuse .cfg and .conf, so I always just look for menu.lst. If that exists, you're on Grub Legacy. Now, the thing about Grub is it's kind of difficult to modify. It's very easy for automated systems, like when you install a new kernel, to figure out how to update the menu and update the boot code. But it's really difficult for the end user to modify that stuff. And the boot menu, usually when it's booting up, it says, press something in 10 seconds in order to change the way it boots. So this usually just appears for you and you can see it. Now, Grub 2 is a lot more customizable. In fact, if you go into the etc. default Grub file, this is a configuration file that's easy to read, and it's going to allow you to change the way that it looks when it boots up. Now, Grub 2 also has a ton of other cool features. It can boot from an ISO file, from a USB disk. It can name, or it can identify hard drives based on their UUID or their device, like DevSDA. So it's a lot more advanced than Grub 1. But one of the advancements that's also a frustration is that boot menu that I talked about that comes up with Grub. It's hidden with Grub 2, so it just goes right to the login screen. You never see anything from Grub 2. And if you don't know this little trick, it can be a real bugger to get into that menu if you want to change something during boot. So be sure to just hold down the shift key when the computer is booting up, and then boom, all of a sudden you're going to get into the Grub 2 interactive menu that you can change boot code things on the fly. It's really, really cool. I'll show you what I mean, but it's not difficult once you know if you have Grub or Grub 2, which allows you to do a lot more configuration stuff. Now, I'm here on an Ubuntu system. This has Grub 2, and if we were to look at, let's just look at it, etc. default Grub, we're going to see this is just a configuration file. We can change these things. Once you make a change, you do have to do sudo update grub. When you do that, it's going to update the boot code inside the boot folder. And if we look in that boot folder, so go into boot, grub, type ls. Well, look at that, grub.cfg, there's no menu.lst, so we know that this is Grub 2. So that's how you manage things in Grub 2. I'll show you really quickly before we end. This is a computer that's turned off. If I start this computer and hold down the shift key, as long as I hold down the shift key, boom, we get this menu. But if I don't hold that, we don't see any menu for us to interact with Grub at all. Now, figuring out if you have Grub or Grub 2 can be a little bit challenging if you don't know that simple trick to look for menu.lst. But they both do the same thing. They tell the computer how to boot up and how to mount its different partitions. It's just that Grub 2 is definitely an advancement. It's more configurable, it does more things, and it's easier for the end user to manage. I hope this has been informative for you, and I'd like to thank you for viewing. Linux is so flexible. It can boot from an incredible number of methods or sources. Now, there are several different things we need to understand about the boot processes, like is it hardware based or is it software based? And I'll tell you what I mean about that in a minute. But there are just this multitude of ways that a Linux system can boot. It can boot over PXE or Pixie boot. If you haven't seen that, it's just the coolest thing ever. It's when it boots up completely over the network. We can boot from USB, from CD. iPixie is a more advanced version of Pixie. I'll talk about that too. And then ISO images, just like the .iso file, you can actually make a grub2 entry that will boot directly from the ISO, even though you don't have it burned to a disk or to a USB drive. It can live on your system, and you can have a grub menu item that boots directly to that ISO image. It's really flexible what it can do. But that hardware software thing I wanted to talk about, because where the boot process is taking place is really important. Some of it is Linux specific, some of it is not. So first of all, let's talk about the hardware things. Now when I say hardware, I mean the BIOS or the UEFI, the part that takes place before Linux is ever introduced. And PXE is one of those things. PXE, which stands for Pre-Boot Execution Environment, is the way that the hardware says, okay, I don't see a hard drive, or I'm not set up to use a hard drive, so I'm going to query the network. And it just queries a DHCP server, and the DHCP server responds with not only an IP address, which is what DHCP servers normally do, but also a boot file and a TFTP location. A TFTP server is just a place you can store files on a network. And then basically the computer then downloads that image, that boot image, from the TFTP server, and that's where Linux comes into play. That kernel or that boot file is the Linux kernel, so it downloads it off the internet, off of your local network, and then it puts it in memory and boots itself from there. So PXE starts as just a hardware thing and then turns into a software. There's also iPXE, which is very similar, but instead of using TFTP to download that thing, it allows you to use HTTP, which is faster and usually more reliable than the old-fashioned TFTP. But it's very similar in concept, iPXE, if your computer supports it. Then USB, this is also right on the hardware. Now the hardware determines exactly how to boot from the USB, but on the USB itself is where the Linux code is, right? So the hardware knows that it can boot from USB, same thing with CD, and to be quite honest, same thing with a hard drive, right? The hard drive is booted to because the computer itself understands how to do that. But when Linux comes into play, we'll say the software side of things, this is once it loads into Linux, Linux does some things on its own, like the ISO booting with grub2. That's after Linux starts, right? Or after grub starts, it says, okay, I'm in grub now. What are we going to do? We're going to either mount a partition, or we're going to look at this ISO file and actually use that as our operating system, just like it was burned to a CD. So some of this stuff is software. This is where you select a kernel. This is where you can have memtest. So a lot of the stuff is done in software, but most things, actually all things, have to start in the hardware. Otherwise, you're never going to, get to the point where the software takes control. But it's important to know that PXE, iPXE, these are not Linux specific boot methods. These are boot methods the computer supports that Linux also supports, in that they can provide the boot file. So I don't want you to confuse PXE, network booting, with something specific to Linux. Same with USB and CD. We can boot Windows from USB or CDs, and it works, because the hardware supports it. If I'm honest, probably the most fun way to boot a computer is using PXE, only because there's no media, right? It just boots directly off the network, and for some reason that's just really awesome to be a part of. It's really awesome to see. But there are multiple ways that you can boot Linux, and it's important to know that they're all there. It's okay if you don't know exactly how to, boot from an ISO file using grub2. Anybody's going to have to Google the specifics of that in order to make it work. But knowing all these different processes exist for booting a computer, that's vital, because that will help you learn and help you troubleshoot when you run into a booting issue. When it comes to actually booting the Linux kernel, there are a lot of problems that need to be solved. And it's sometimes sort of like a chicken and an egg scenario. You have to do one thing, but you can't do that thing until the other thing is done. And what do you do first, and how do you do it? It can be really confusing. But basically, we want to get the full kernel with all of its modules running. So the boot process is very complicated, and it might seem overcomplicated, but the issue is to try to get the kernel running and then allow it to access the modules that are stored on the hard drive on your system. And it ends up being, like I said, fairly complicated. And if I'm honest, I've been system administrator for over 20 years. I've passed lots of certification tests, and I have never fully understood every step of the process of booting the kernel. So you're going to be like the king of the next nerdy party that you go to, because you're going to know all the Trivial Pursuit answers when it comes to Linux kernels. So let's look and see what the boot process actually is, and then I'll show you on a system where those files live. So I have sort of a little flow chart here. Now, a lot of these steps we probably are already familiar with. First, the computer either has BIOS or UEFI, and that's the hardware on the computer which looks for something that Grub or Grub2, it's one or the other here, will provide. And then that boot code of, that Grub uses points us to the kernel. Now, this is the stuff where it starts to get a little, not confusing so much, but complicated. It's almost like this fine dance that has to be done. Now, what the process is normally is we have the actual Linux kernel itself, which is a file, one file, and it's called VM Linux. Or you'll probably currently see it called VM Linux with a Z. And the only difference here, these are the same file. The only difference is that this is compressed, right? The Z means that it's compressed. So it's just a space saving method. So usually we use VM Linux just to save some room on the system. And then this is the kernel itself with no modules, right? So there's no modules. This is just the base kernel. And then once the kernel boots up, it will mount all the file systems, and then it will have access to all of the modules that it needs to insert to make things work, like, your USB mouse and your keyboard and your monitor and your video card. All those things are modules that are loaded into the kernel. They're not part of the static kernel, right? I mean, we could build this huge kernel that includes everything, but that's just a waste of resources. And so we have this stripped down kernel that has just enough stuff to make sure that we can mount the file system so that it can have access to all of its modules and then become the full running kernel on our system. There's a few problems. What if this full kernel and all the modules, so basically what if all the modules here are on a file system that this stripped down kernel doesn't know how to mount, right? It's like, well, I don't know how to get onto a RAID device, or I don't have any idea how to mount this fancy new SSD drive that you put into the PCIe slot or something. Well, that's where initrd or init RAM disk comes into play. This is just enough information, like module information and driver information, to be able to have the Linux kernel access the file system so that it can get to its modules. So rather than make, a custom, a bigger kernel for every specific system, what we've done is we have a generic stripped down kernel, and then this initrd has the stuff we need in order to load the modules by mounting the hard drive, or whatever we need. Maybe this is stored on a network drive, so we have to have the NFS stuff in order to mount a remote disk on the computer so it can access its modules. So this is just like the temporary staging area for kernel stuff that we need, and this is kind of inserted right into this running stripped down kernel. Okay, now I want to mention this because a lot of people confuse the init RAM disk with the init RAM file system. And they seem similar conceptually. They are fairly similar conceptually, except that the init RAM FS is actually part of the actual kernel itself. It's part of this VM Linux or VM Linux kernel. And this is, just like it says, it's a file system that it creates and mounts in RAM. And I want to mention this tool, even though we're not going to go into it much. Dracut is a tool that has made this extremely generic using UDEV and stuff like that, so that it's very flexible. But this is basically the tiny little file system that the Linux kernel uses in order to do what it needs to do to get to the point where it can load the full kernel by loading modules. So initramfs is a file system that it loads into RAM, but that's part of the kernel itself. This initrd is a RAM disk that is mounted alongside of the kernel that allows it to get to the point so it can use the full kernel. Init RAM disk is not used after the system is booted up. This is just like a temporary staging ground to get to the full kernel. Wow, that was a lot of information, but it's really fairly straightforward when you see why it's doing all of those complicated things. Now, I want to show you really quickly some of the files that we talked about. So here I am inside Ubuntu, and this is the boot folder, and we can see we have, here's the initram, sure enough, and this is, I have a couple different kernels in here. There was an update, but the kernel numbers are listed here. But here's the initram disk, and here is the actual kernel file itself. There's a couple other files. The system map actually tells the kernel where on the file system all of its modules live. And then config, this is the configuration file when the kernel was actually compiled. So if you want to see the options that were used there, but those are the main files that are on the system. One other thing I want to show you is this system.map tells the kernel to look in lib modules and then the name of the actual running kernel, and inside there is where you'll see the actual different modules. Okay, and this is where the modules that are going to be loaded in to get that full kernel live. So that's the basics of starting a Linux kernel on your system. Now, I know we covered a lot of things and a lot of terms and a lot of concepts, but they should make sense once you go through that flowchart of what's happening and why it's happening. And in the end, which comes first, the chicken or the egg? Well, it depends on what you need to do, right? If you need an egg, then the egg comes first. If the chicken can handle it on its own, no eggs are needed. Now, a kernel panic certainly seems like a really good time to panic, but I assure you, just because the kernel panics doesn't mean you should, soldier. But really, kernel panic just means that something went wrong with the kernel. Now, there's a couple common causes, and there's a couple things we can do depending on what the root cause is. Now, if all of a sudden you're starting to get kernel panics and you haven't done any system updates recently, and it's kind of hit or miss, it'll happen, it won't happen, it happens when you're doing something but not another, chances are you may have a piece of faulty hardware. And this is one of the really common ways that you can experience a kernel panic. If you have an overclocked CPU, for example, that can sometimes cause kernel panics. A bad stick of RAM is another one that'll really do it. And, some add-on card, like video cards are sometimes, guilty of doing this. Really anything on your system, any hardware, if it fails, it can cause a kernel panic. There's a couple ways to, try different things, especially if you have multiple sticks of RAM. Sometimes you can pull out a stick of RAM, see if you still get a kernel panic. If you do, then put that stick back in and keep pulling them out one at a time and see if the kernel panics automatically go away when you remove one certain stick. Hey, chances are that's what's wrong with, that certain stick is a bad stick of RAM. It can be frustrating to track down hardware-related kernel panics, but there's also another very common kind of kernel panic that happens, and that's when you upgrade your system. So let's say that you just ran a system update on your system and it installed a new kernel. You reboot the computer and then boom, it says something like failure to init or kernel panic, blah, 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 blah. If that happens, there is something that you can do, which is fairly easy to do, and you can, rescue your system, so to speak. So when it boots up, we're just going to go into Grub and we're going to pick an older kernel, because when you update a system, it keeps the older kernel for this exact reason. If something goes wrong, you can pick a different kernel and boot the system and then fix it. So I'll show you what I mean. Here we are on our Ubuntu system, and let's say I just recently updated it, and during the update it says now I need to restart my system. So I'm going to restart the system and everything should go well, blah, 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 blah. And then boom, we get a kernel panic. Now this doesn't actually give us the words kernel panic because I did something fairly simple to simulate what would happen if there was some corruption in the kernel. But it says here, it's unable to find the initrd. Sometimes you might see kernel panic init or unable to kill init or something like that. It says press any key to continue, but there's nothing that's going to happen, right? It's kind of locked up on me because it errored out. There's no initrd. So what we're going to do is restart the system. And when we do that, we're going to initiate the grub menu by holding down the shift key. So first of all, we do need to restart the computer. I'm going to hold down the shift key and we should get presented with a grub menu. Sure enough, here's our grub menu. Advanced options, and we're going to see here we have multiple kernels. This is the kernel. The newest one is the one that it tried to boot by default. So I'm just going to go back to the last successful kernel that we had. Press enter, and it should boot this up, and our system should be just fine. Then all we need to do is remove that kernel package with the failed thing using our apt system, reinstall it again, do an update so it reinstalls, and then it should install that, init back in place, and we should be fine. So it's nice that Linux keeps a few of the older kernels kind of in line so that we can do exactly this. If something goes wrong with one kernel, or we've deleted modules, or just something doesn't load, or we get a kernel panic, we can select a previously successful kernel, and then here we are on our system working perfectly, and now we can go through and remove that package and fix it, etc., etc., etc. So if you do get the kernel panic, especially on a production system, it can be really scary. But know that there are ways, to fix it. If it's just a kernel corruption, you can boot to a previous kernel. If it's a hardware issue, it's a little harder to troubleshoot. But you can also do something like boot from a USB drive or a CD, and at the very least, you'll be able to access the hard drives so that you can get stuff off of your computer if it is a hardware failure that's causing the problem, and then you'll have your data to put onto a new computer. But kernel panics are no reason to panic. It's just one more thing that we need to understand how is working so we can fix it or troubleshoot the problem and move on from there. We know that the Linux kernel is modular in that it doesn't load all of the drivers that it could possibly ever need automatically by default. It has these modules that it dynamically loads when it discovers that it needs, like a driver for a certain sound card on boot. Now we can configure it to automatically load those modules by setting it up in a config file, which we're going to look at. Now what happens though is it'll load that module, but then behind the scenes there's some incredible dependency checking going on, and that dependency checking is really, really good at knowing what modules a particular module will depend on. There may not actually be a robot called Modbot in your system or even in my system. I just like to think of a cheesy robot plugging in different modules in my computer. But nonetheless, the computer is really good at finding dependencies. In fact, sometimes it's too good and we need to blacklist certain modules so that Modbot doesn't say, oh, this one will work, and put it in. I'm going to show you why we would do that and also how to do that. But we're looking at two concepts today: how to automatically load a module on boot, and how to make sure that the wrong module isn't loaded on boot automatically by the system detecting a dependency that you don't want it to use. Now here on this is an Ubuntu system, but all Linux distributions have kernels. We're going to go into the etc folder, and there's a file here called modules. So we're going to look at that. We can see right now it's empty. It says kernel modules to load at boot time. This contains the names of the kernel modules that should be loaded at boot time, one per line. Lines that begin with this are ignored. So what we would do is put the name of the module, and we would add something like E1000, which is the name of an Intel network card module. Now, normally the system automatically detects the hardware and it knows what to load, but I want to give you an example of how you can manually load a kernel module and have it done automatically on boot, even if the system doesn't, detect it on boot, like, oh, I have new hardware, I need this particular module. So this is how you would manually do it. All right. Now we're not actually going to save this because I don't want to load that module, but let's say that's loaded. Now, if there are dependencies, it will also load those dependencies. Let's say that the Intel E1000 network card also requires the PCI bus to work. Well, then it would load the PCI bus module. So it's really smart. But let's say that there are two different PCI modules. There's like PCI version 1 and PCI version 37. And by default, it's going to load PCI version 1, and we don't want that. So what we would do is blacklist it. So if we go into etc modprobe.d, first I want to show you there's a bunch of files in here. Anything with .conf is read in, right? So it doesn't matter which one you put it in. There's just some conventions here. Anything we're going to manually put in, we're going to put into blacklist.conf. So let's actually edit that file. And we're going to see there are a bunch of things that are already blacklisted. Now, what this does, it just makes it so that the kernel doesn't automatically load it. Like let's look at this Ethernet one, okay? So this is an ETH1394. This is a FireWire network device. All right, it's saying here we never want to use a FireWire network device. So if you detect a FireWire device, I do not want you to load the ETH1394 or the Ethernet module for a FireWire port. So if we put blacklist here, it's not going to load it. Even if we put in the FireWire module itself so that it activates that port, this will make sure that the kernel or modbot or whatever, however you like to visualize it, doesn't say, oh, well, you're putting that in. Why don't we also activate the Ethernet ability of that port? We don't want that, so we put blacklist in here. Same thing like that. I've done this the most with sound cards because there are like 150 different sound card drivers for the AC97 model of sound card. So a lot of times you have to blacklist a bunch of different models, and see there's a blacklisted sound card right here, right? This is saying don't load this module. That's not what I want. And this looks like it's because of an Ubuntu bug. All right. So anyway, this is where we tell it what not to load. Even if it's compiled in and it's part of the module, we would put it in here or any of the files in this folder. Anything that says blacklist space blank is going to be blacklisted. Honestly, like I mentioned, the Linux kernel is usually really good at automatically detecting hardware and loading all of the modules all on its own by detecting new hardware on the system. But if there are times where you want to manually load something, but you want it to be done on boot, that's where we would put it in the etc modules file. And then blacklisting is really important, especially if you're having problems with something like, it just doesn't work with this kernel module. Let me blacklist that so the kernel will pick another module and try to activate that one. One of the things that makes the Linux kernel very special is that it's modular. So we don't have to install all of the drivers for all the potential hardware in a system. We just install the drivers and the modules for the things that exist. It makes the Linux kernel very efficient because we don't have all that bloat, all those unneeded things sitting in memory where they're never going to be used. So the kernel can be very, very efficient because of its modular design. But in order to take full advantage of that, we have to make sure that we're putting the right modules in the right place with all the dependencies, so we don't end up with a kernel looking like this, right, with pieces that don't belong. Thankfully, there are a handful of tools that we can use to properly manipulate the kernel modules. And the first two I want to look at are insmod and modprobe, because on the surface they appear to do the same thing. Insert modules into the running kernel. This is after we're booted. It'll insert them into the running kernel. So let's compare them to scientists, right? So insmod is a very basic program. You have to give it the full path of the kernel module that you want to install. It doesn't do any dependency checking. It just kind of slams it into the running kernel. And if the kernel doesn't work, like it's the wrong kernel version or it doesn't have the proper dependencies, it's just going to fail, and it's not going to give you an explanation as to why. It's just going to say, well, I crammed it in there and it didn't work. Boom. But modprobe, on the other hand, is a more advanced program. It's a more efficient model. And what it does, you can give it just the name of the kernel module. You don't have to give it the full path. You can give it just the name of the module itself. It will look and determine all of the dependencies that that module needs. So if one module needs, depends on another module, it will say, oh, let's load that other one first. It does a really good job. Now, it does need us to have a map of all the needs and dependencies on a system, but there's a program to do this. We just make sure we type dep mod when we're done installing a new kernel module, and it will recreate that map so modprobe knows where to find the dependencies. Now, you might be thinking, okay, well, obviously I'm going to use modprobe when I insert modules, and exactly, that's what you should do. Why does insmod even exist? Well, here's the deal. Modprobe actually knows what modules to install, and then behind the scenes it uses insmod to do the actual inserting. So modprobe is really kind of a front end that's very intelligent about what to do on the system, but that's why insmod still exists. It's still the basic tool that is used to cram modules into the running kernel. Modprobe just knows which kernels to load and in what order to load them. So modprobe is what the humans use, and insmod is what modprobe uses, if that makes sense. It's really easy to see that in action on our system. So I'm root on Ubuntu here, and let's go into lib modules, and we're going to see we have folders for each of the kernels installed on the system. We're going to go into the one that we're currently running, which is the latest one. And inside here, we'll see this is where we have a lot of like the map files for the modprobe, so it knows where the kernel modules live. Let's go into the kernel folder where the modules live. Type ls. Let's go into the drivers folder. Type ls again. Oh, there's still a lot of drivers. Let's go into the net folder. All right, there we actually see some kernel modules here. Okay, so we're going to play with Thunderbolt-net. But let's say we wanted to load this in so we could use Thunderbolt as a network device. If we wanted to use insmod, we would say insmod lib modules generic kernel drivers net Thunderbolt-net, because we need the entire path. We're going to press enter, and it's going to say, well, I can't do that. Unknown symbol in module. It doesn't work, blah, blah, blah. It has a dependency. It doesn't tell us what the dependency is. But if we were to use modprobe, and we were to say, modprobe, I want you to put in Thunderbolt-net, and that's all. We don't have to say a path. We don't have to put KO at the end. Just press enter. Boom. It's automatically installed. How do we know? Well, one, we didn't get an error. It just installed it. But if we type lsmod, will show us all the installed modules, and if we scroll a bit to the top, we're going to see, well, look at that. Thunderbolt-net is installed into the running kernel, and we can see the dependency was Thunderbolt, but modprobe knew to do that, and it installed it. Now, there's another tool for removing them, and that's rmmod. Now, there's no super smart version and dumb version of these. rmmod is kind of halfway between, because if we were to say rmmod Thunderbolt, it's not going to do it. It's going to say, I can't do that. It's in use. But at least it tells us what it's in use by, right? Thunderbolt_net, which that's a little strange because the name of it doesn't have an underscore, right? If we want to get rid of this, we could say first we have to rmmod Thunderbolt-net. Okay, no errors. And now if we do the up arrow twice, now we can rmmod the Thunderbolt module. And again, no problems because we got rid of that dependency first. So now if we do lsmod, we're going to see, if we scroll up, that they're not in there anymore. They're not installed into the running kernel. And that's how you can manipulate kernel modules on your system. Some of the tools are smarter than others, but it's really important to understand why they're smarter. And like insmod is important still, even though you don't want to use it on the command line for doing very much at all. Now, one more thing I just want to tell you about is if you install a new kernel module, like you download a piece of hardware and it has its own kernel module and you compile it, and so then you have the kernel module and it's put in this folder, you know, so that it's in our current running modules folder, you have to type depmod in order for it to update that database or that system map so that modprobe knows where it lives and what dependencies it might have. It takes a while, and now we have it updated, so now we can install that new kernel module because it knows all the dependencies on the system. Now, I know in the picture here, I have these, wrong puzzle pieces put into the puzzle. This is actually a lot harder to accomplish than you would think because the tools just fail, right? They say, oh, this won't fit, or this is the wrong kernel module. Some of them are smarter about it than others, but it's really difficult to put the wrong kernel module into a running kernel. But I want to make sure that you understand all of these tools exist, how they work, what they look for, and the difference between them. First off, we're talking about network connectivity today, and the first thing I want to show you is always check the cable. Now, it seems silly, right? Of course the cable's fine. This is plugged in just fine. However, see, it wasn't plugged in tight. And whether it's a jokester in the office or somebody who ran over a cable with a vacuum cleaner or something, sometimes it is the cable, and you can spend a ton of time on the command line and be very frustrated to discover that it was just a bad cable. So that's just a pro tip. Check the cable, make sure it's plugged in tightly, and that the little lights on the back are flashing and doing their thing. Now, we could probably do an entire course on troubleshooting a network connection that's not working or not working right. But today I want to go over just a couple quick tools so you can determine very quickly what your issue might be on the network. So I want to look at ping and then just to check out our address on our computer. And so the first thing I want to do is give you this scenario. We're on the computer and we're trying to go somewhere like Google, and it says unable to connect. Oh, we can't get online. So the first thing I would do is open up a command line window, and I would say, let's try to ping Google. So ping google.com, network is unreachable. Okay, well, I know that the Google DNS server has an IP address of 8.8.8.8. So that's the next thing I would do to eliminate whether it's DNS, right? Maybe it's DNS that's not working. So I want to see if my network itself is working. So I'm going to say ping 8.8.8.8. Network is still unreachable. Okay, so there's an issue with more than DNS. That means that there's a problem with my network. So let's look and see what our network address looks like. Now, there's a couple tools. You can try to type ifconfig. If this doesn't work, see, it's not on my system. It's a newer system. So type IP add for address, and it will give you the IP addresses on your local computer for your network devices. So this is the local host 127.0.0.1. This is just like a virtual host that says it's local. So we don't want to use this one, but this is our Ethernet port, right? ETH0, and it looks like we have an address of 10.10.10.10. So I would say let's ping that. So let's make sure that, our network stack itself is working. Yeah, okay, so this is working. I can ping my own IP address. So the IP stack itself is working. I'm going to hit Control C, but for some reason I'm unable to ping out of the network. Now let's assume that my gateway address is 10.10.10.1. Ping 10.10.10.1. Okay, I can ping other computers on my network. So it's not, well, first of all, we know it's not my computer cable, right? Because I can ping a different computer that's across the network, but I'm still unable to ping Google. So for some reason, my internet connection is down. Well, let's look at our IP routing information. I'm going to type IP space route and press enter. All right, it looks like 10.10.10.0-24, so this network is directly accessible via ETH0. Okay, so that's working. That's why we could ping this up here. But if you'll notice, now you might not notice, but there's a line here that's missing. We don't have a default route set. So that means that the computer, while it can access other network or other computers on our local network, it doesn't know where to send packets that are destined for another network. There's no IP routing information here. Now, if this is an IP routing nugget, I could say, okay, let's add a route manually, but this is more of a troubleshooting nugget. So here's the deal. Probably when we got our DHCP address, we didn't get all the information or something fell apart. The first thing you do is either turn it off and turn it back on, right? That's the standard IT guy response, right? Well, in this case, it might work. Or we could actually go and just go to our wired network interface here, turn just the network interface off, connect again, turn it back on. And now let's just look and see what our IP route information looks like. Look, when we brought our network interface down and back up, now we have a default route added. So now let's see if we can ping google.com. Boom, we're able to ping it. We go over here and we should be able to access Google as well. And sure enough, there's Google. So we've successfully troubleshooted the problem with our network connection. In our case, it was a route thing. And really just turning off the network interface and turning it back on was the way to solve it. But the important part is going through the process of determining where the problem is. We knew it wasn't a network line or the network cable because we were able to ping other computers on our network. So it's just a matter of troubleshooting and going down the list of where can I connect, and what might cause those issues. Figuring out connectivity problems is sometimes more of an art form than it is a science. You just have to kind of put yourself in the mindset of a packet and say, okay, what information do I need to go from point A to point B, and what is stopping me from getting in between there? Tools like Ping are able to make sure that you can or can't connect to remote computers, and then using the IP-ADD, you can see what your address is. We also used IP route to look at the IP route information, and that's where we discovered we didn't have a default route. But tools like this are what you can use to troubleshoot your connectivity to figure out what's going on. But don't forget, always check that cable because sometimes it's just a physical cable unplugged. DNS, or domain name system, is the way that your computer converts a URL or a domain name like google.com into the numbers, the IP address that the actual computer knows how to connect to using IP routing. So google.com isn't really helpful for anything except for DNS. Really what the computer needs is that IP address so that it can get there. Now there's a couple tools that we can use to test DNS on our system. One of the most common is Ping, right? You just ping and see if it can reach it. If it can reach it and get a response, hey, it's working, great. But there are three other common tools that I want to cover: Dig, NSLookup, and host. And let's actually look at those individually because they all do about the same thing, but they do it in a slightly different way. Now, Dig is the program that I use most often only because it has a cool name, right? There's really no reason that I use it other than the word dig is just kind of cool. So Dig, you type Dig, and then you can just type the host you want to look up, like diggoogle.com, and it will use your default DNS server and look it up. If you want to specify a DNS server for it to use instead of the one that your system is currently using, which is a way that you can test your particular DNS server, you put the @ symbol and then the IP address of the server that you want to query. Now, the other two programs can do the same thing. They just do it in a different order. You can say nslookup and the host you want to look up. And then if you want to specify a server, again, you don't have to, but if you want to, then you put the server after that. Same thing with the host command. You type host, the host name you want to look up, and then if you want to specify a server, you put it there. If you leave it off, it'll use your default. And they all, like I said, do kind of the same thing. So let's look at them really quickly, and then I'll talk about how to query different servers and do just a little bit of troubleshooting on your system, because testing DNS is kind of vital if you want things to work on your system, and they don't seem to be. So first of all, let's look at them all, how they function just by default. So I'm going to say dig google.com. All right, and this is the response I get. It's queried my default server, and we can look. My default server is listed right here, 8.8.8.8, so that's pretty awesome. And this is the response it gets. There's a bunch of A records for google.com. Now, let me clear the screen. We can do the same thing with nslookup google.com, and this is going to give us a little bit different format, right? It says our server right here. This is the, I highlighted the wrong line. That's our server, the same server. Of course, it's our default server, and it gives us all the addresses. These are all the A records. A little less detail, but it gives us the same information. Now, if somebody tells you that nslookup is deprecated and it's not used anymore and it's going to be abandoned, there's a weird case with nslookup. That's true until it wasn't. They were going to get rid of nslookup and replace it with dig, but then they came out with bind 9.3 and for some reason decided that nslookup was going to stick around. So we have nslookup and dig. And lastly, let's clear the screen again. We can just say host google.com, and this will give us information as well. It actually doesn't tell us what default server it's using, but it gives us a lot of information. These are all of the A records for it. These are all, the IP addresses. This one actually also tells us the mail handlers, the MX records for google.com's domain, which is kind of interesting as well. So just pick the one that you like the best, and that's what you can use. And the reason that it's important to pick one that you like and use it often is so that you're comfortable with it, right? Like I said, I usually use dig, and that's weird, I know, because it's the least common way to handle specifying a server, right? The other two you do, like nslookup, what you're looking up, and then a server. With dig, you say dig at, and let's say 127.0.0.1. That's localhost, right? So dig at localhost for google.com. And we got a response, okay, google.com, and it gave us this address, which is different, but it came from our local server. Now, it did not get all the same responses that we got from the 8.8.8.8 domain server, our default domain server. If we were to say dig at 8.8.8.8, google.com, we would get a totally different set of IP addresses. So that's why it's really important to be able to query different servers so that you can get different responses. Because on this computer, if we tried to ping google.com, it's going to try to ping that other address and time to live exceeded. It's not ever going to work. So there's something wrong with the DNS server running on localhost. Now, I'll show you what the problem is. The hosts file, I've actually sabotaged here. This is the etc hosts file. This is where your computer will look first for any DNS lookups. And sure enough, I've kind of bamboozled it here. I put the wrong IP address for google.com. So I put that in there. Now if I restart our local server, now if I try to ping google.com, it's going to be just fine because it's going to actually use the real address that it looked up on the internet. But that's how you can use the different tools to specify not only what host you want to look up, but what server you want to query when you look it up. So whichever one of these makes the most sense to you, or whichever formatted results you like best, just pick one and use that, because you can specify a server for each of the different commands. But knowing how to use them is important because troubleshooting usually means querying more than one DNS server so you can figure out what the heck is going on. One of my favorite things about Linux is that everything is configured with text files, right? It's just plain text files. It's awesome. And the network is no different. It's configured with text files. Now, There are a few differences when it comes to distributions. If you're on Debian or if you're on CentOS, there are going to be some configuration files that are different because they configure their networks different. Now, there's nothing wrong with being unique. I really like the differences in the distributions, but there are some files that are consistent regardless of what distribution you're using. We're going to call those the common files, and that's what we're going to look at in this nugget. These files here are consistent across the board. They're just kind of standard Linux files. So I want to show you what they are and where they live and how they are configured and what they do. And that's, again, just the common files. There's going to be specifics in the different distros, but we're just looking at the files that are common to Linux in general. In this case, we're going to look at the files in Ubuntu. And the first one I want to look at is the etc hosts file. So let's actually become root. If we want to edit them, we have to be root to do so. So I'm going to look at etc hosts. There's no extension at the end. It's just etc hosts. And this is a file that acts kind of like the first resort DNS lookup. So before a system even looks things up via DNS, it looks in here. And there's a couple things here like localhost and Ubuntu, this is our host name, are set up in here. But we can add something. We can say, what if we wanted to make sure users were never able to go to Google? We could say, okay, 127.0.0.1, which is our local host, is now going to be google.com. So if somebody tries to go to google.com, they're going to try to hit our local machine, and we don't have a web server at all, so it's just going to error out. So if we save that, now on our computer, if somebody tries to go to Google, it's going to fail. So google.com. Unable to connect. Even though our network is working just fine, we could go to Yahoo if we wanted. It's just a matter of that DNS entry in the etc hosts file that we kind of broke. All right, so another place we can look is in the etc ns-switch.conf file. Now this configures a bunch of things on our system like group and password files, but what I want to show you specifically here is the hosts line. So this is saying where does it look for DNS lookups to find what the host's IP addresses are. The first one is called files. This points to etc hosts. If we have this listed first, that means before it queries a DNS server, it's going to query that file. It's going to look in that file first. And then in order, these are what it's going to do from there. It's going to do, the MDNS for local lookups, and then it's going to use a DNS server. So this is the order that it's going in, but the first one it looks in is the files, specifically that etc hosts file. So you can change the order of that. I don't recommend changing the order because that's kind of what we want it to do. But one more thing I want to show you is etc resolve.conf. And this is a little bit of a confusing file because while this tells the computer what name server to use, you'll notice up here it says do not edit this file. Now back in the day, you would just put name server and then the name server you wanted to use on your system. But now this is all handled with the systemd resolved service, and it creates this file on the fly. So really we do not edit this at all. Network Manager handles all of the name server entries in here, or whatever your distribution uses for configuring the network. So we don't actually edit this, but if you want to see what server your particular computer is using, you can look in here, and it looks like it's querying 127.0.0.53, which is another IP address to our local computer. So that means that it has some sort of local caching DNS server, and it's not querying directly to the internet. Now, you probably noticed that all of these common files have to do with DNS, and that's fine, but it's interesting that DNS is kind of commonly configured across the distributions. When it comes to actually configuring the individual network devices, that's drastically different from one distribution to the next, but the common files are generally DNS files, and that's what we looked at in this nugget. Ubuntu is one of the most common distributions out there, but it's based on and built upon Debian. So when we look at configuring one, it's very similar to configuring the other, and that's the case with network files. Now, I want to show you where to find the different network files on an Ubuntu or Debian system, but it's important to note that in the last iteration of their long-term support for Ubuntu, that's when a change has been made to how the network is configured and what files are used and how those files are configured. Now, there is one commonality between them, and that's if you use Network Manager to manage your network instead of editing the configuration files. That hasn't changed. You can still use that across all the versions that are current with Ubuntu and Debian, but these two ways have changed. So first, I want to look at the older version of Ubuntu. And when I say older, I mean one that's still valid to use as of the date today. You can still use version 16.04. Let's see what version this is. Etc. OS release. So this is Ubuntu 16.04.1 LTS, long-term support, and this is still, as of today, a valid version of Ubuntu to use in production. But this is configured by going into the etc. network directory, and there's a single file in here called interfaces. So if we look at interfaces, we're going to see this is how you configure a network interface with an older version of Ubuntu or Debian. Now, this is pretty much the stanza that you configure. There's usually something in here you can look at and base it off of, but this is the format for it. We're not going to go through the, configuring different things. It's pretty straightforward. You don't have to indent. This is just for ease of readability, but this is how you configure a network interface via the configuration files. Now, we could still use the network manager if we were on a GUI system. Like this is a GUI system, we could use that, but I'm actually SSH'd into a server that doesn't have a GUI interface, and that's where we use these network files to configure it. So let's quit this one. This is how you configure an older version, but a modern version like 18.04 or the most modern version of Debian uses a completely different network configuration system. Now here we're on a newer version of Ubuntu. This is actually 18.04. Let's check that out. So this is 18.04.1, another long-term support release of Ubuntu. And this one uses the net plan system for configuring network interface. So if you go into etc. net plan and you look in here, depending on what kind of system you have, you're going to have some sort of file in here. It's either going to be like 01 networkmanager.yaml or 50 cloudinit.yaml if it's a server. The thing about YAML files, though, let's look at this. YAML files do depend on indentation in order to be properly configured. So while with the etc. network interfaces of the old Ubuntu system, it didn't matter how things were indented, here it really, really does. And so here, this is where we would configure like a static IP address. And we, here's our IP addresses, gateway, name servers. The format's a little different, but it's fairly similar conceptually to the old system. Like I said, except for that white space. That's really important that it's indented properly. So if you make a change to this, then you just would do sudo netplan apply, and then it will activate the new changes that you made. Now, I do want to point out, again, this is a GUI system, so it has Network Manager, but there's also NMTUI, which is Network Manager Text User Interface, and then you can edit interfaces using just the text boxes on your screen if you don't have a GUI system installed. So that's just one more way that you can edit your file in Ubuntu or Debian if you don't have a GUI, but you want to use Network Manager as opposed to just configuring those files on your own. Whether you have an older system using etc. network interfaces or a newer system using configuration files in etc. netplan, configuring the network on Debian and Ubuntu is not difficult. And, it's usually just a matter of changing what's existing. But if you want to use the network manager to manage all of those interfaces, either using GUI or text tools, you can do that as well. It's very flexible, and even with the change in versions, it's not a whole lot more difficult to do one over the other. If we've been learning together for a while, you know that I prefer Debian-based distributions, and Ubuntu is my jam. But I have to admit, when it comes to network configuration files, CentOS or Red Hat, they really have an elegant solution for how to configure the network, and there's no confusion between if you're using the GUI network manager or if you're just using the configuration files in the etc. sysconfig folder. Let me show you what I mean, because CentOS is just so awesome when it comes to network configuration. Now, here we are on a CentOS system, and it doesn't matter which way you configure the network interface. You can go up here and go into the network manager to configure it, or we can go directly into etc. sysconfig, And I just wanted to show you quickly, inside the sysconfig folder in CentOS is where all of these configuration things are. This is kind of unique to CentOS and Red Hat. They put most of their configuration inside this etc sysconfig folder. But inside here, there's also another folder called network scripts, and that's where our networking is configured. If we look in here, we're going to see there is this configuration file for our interface, ifconfig-eth0. So let's look at that. If we edit this, it's going to change the way our network interface comes up. Like if we were to change boot proto from DHCP to static, and then we were to add a line IPADDR equals, let's say 10.10.10.111, which is not currently the IP address. If we were to do that and save it, and then just do a quick sudo service network restart, we would be able to restart our service. And if we were to do ifconfig, we're going to see, scroll up here. Sure enough, that is our IP address now. Now, there are a couple problems. We didn't